There to apply your math 8 feature there, because you do want to get from your velocity into your acceleration vector value. Math 8. And derivative, yeah.
Oh, and the
Hey, vertical tangents is when your denominator is equal to 0. So you're going to be involving your dx dt. Mhm. That's fine.
Sounds fine. All right.
Yeah, yeah. So on the AP exam, you can either truncate, if it was like 0.3956, you either truncate that or you can round. Yeah. You have two options there. All right, keep going. I will accept. Actually, log of 2. Is that numerically?
Double check this.
Yeah, I'll accept it, but on the AP exam,
They want.
they probably want to see that you work out the break. So it's good to know both ways.
Yeah.
Yeah, just understand that process though.
Yeah, no, I'll just do
Okay.
that for now, and if that's like the way the AP.
Yeah.
Does it.
Yeah, all right. But your ways. We know slope is dy dt over dx dt, so we can put them over each other, and then if you want to find the limit as t approaches infinity, we can bring up that denominator as the reciprocal, and then do t approaching infinity. We know the first expression will go to 0 because the denominator will have a higher degree, and then for the second expression, 2e to the negative t is the same thing as 2 over e to the t. If I plug infinity in for e, that's going to cause that denominator to go to, or cause the fraction to go to 0. Inverse sine of 1 is just equal to pi. Sorry, pi over 2. And we know anything times 1 over pi over 2 is still going to be 0. But we do need to figure out, make sure that this is actually a real number, because otherwise, if it's 0 in the denominator, that would be fine. But it's a real number times 0, so we know that we can stay it with a real number at 0.
To just wait this year.
We should need to confirm that this is actually a real number, though. Because if it's not a real number, then this will be undefined.
So we still have, so profile, that's.
Yeah, just confirm that this is actually a real number. Part B. We know that our dy dt is going to have an impact in terms of how high the graph is going to rise. We know that at 2, the y value is -3. So then how far it rises is going to be the integral from 2 to infinity of my dy dt, right? That will accumulate all the rates, all the rates of increase, and it will allow us to see the path of that vertical rise of my y value. All right, let's go to page 23. Let's try a Taylor series problem. Yeah, this one, we're not gonna, even though it's centered at 0, we're not gonna really be able to use our Maclaurin, uh, Maclaurin expansion for sine. We do need to kind of build this out from scratch. Yeah, and this is technically this is not a calculator.
Yeah, but I'd like you can only do the first one.
Right.
You only do the first one.
So part A, we're just building out our Taylor polynomial. For part B, what's the coefficient of x to the 22? Ideally, we can find the pattern and not have to actually get all the way down to this 22nd derivative. And the pattern is that we're dealing with sine and cosine. They're going to keep alternating within each other after the fourth derivative. So if we divide by 4, we can figure out where the pattern is going to be. So if I divide by 4, if I get a remainder of 0, I'm going to be landing at sine. If I divide by whatever derivative I'm looking for by 4, if I get remainder 1, it'll land here. Remainder 2 lands here. Remainder 3 lands here. And remainder, there's no remainder 4 because it goes back to the beginning. So a way that we can tell where does that 22nd derivative going to land in terms of is it sine, cosine, negative sine, or negative cosine, we divide 22 by 4 and then look for the remainder. So 5, remainder 2. Remainder 2 will land with this negative sign. But you could also just go through each of the derivatives, I mean, all the way to the 22nd, but I think it's just faster if we recognize, oh, there's a pattern, and then figure out which pattern it is. And we know that we're sitting here, and then after the 22nd derivative, chain rule is going to keep pushing that, we'll keep producing a times 5. So it'll be up to 5 to the 22nd. So we know that our formula is going to have a negative 5 to the 22nd, root 2 over 2, all over 22 factorial, because that's my n factorial. So that's the coefficient. Negative 5 to the 22nd, root 2 over 2, all divided by 22 factorial, or just okay, try part C. Lagrange error bound. This is a good one for us to practice our process there for Lagrange error bound. Yeah, I think it's still need to do a little bit of thing there. We'll sign 5x. But that as soon as it gets shifted, then it's a little bit weird. So we know that Lagrange error bounds, we can look at the first unused term, or we can go through our formula, right? F of n plus 1, max out that value. So the fourth derivative, you value at z over 4 factorial. My c is 0, my x is 1/10. And how can I max out that fourth derivative? I know that with sine and cosine, I just have to look at my fourth derivative, evaluate it at 0, which is 625 over root 2. We know this is a safe upper bound, or sorry, safe upper bound is going to be 625 because we know that it's always going to fluctuate. That root 2 over 2 is just going to fluctuate between -1 and 1. So 625 times 1 is a safe upper bound. So they want you to take that 625 there. So 625 over 4 factorial times 1/10 to the fourth. That ends up being less than 1 over 100. You probably don't want to multiply all that out by hand without a calculator. Just trust that this is your answer and say that this is less than 1 over 100. Part D, it just wants you to take the antiderivative of what you've built for part A. Yeah, so typically with beginning to see some of these patterns, right? Anytime they ask you to build some Taylor polynomial, they're usually something that's going to ask you to take the antiderivative, usually, or find the derivative, but typically find the antiderivative. The good thing with Taylor polynomial is that the only integral or derivative rule that you really need to, that you're going to be using a lot is power rule. So typically there's not a whole lot of messy integral or derivative rules, or just power rule. Okay, any questions? Okay, let's use 10 minutes to see if we can make progress with the packet that you just picked up. Let's go all the way back to limits. So a limit tells us the y value that the function approaches from both sides as the function x gets closer and closer towards that number. So it's important that we understand this from both sides. A limit can exist even if the point doesn't exist. As long as we can pick points on either side of our target, as long as the arrows are pointing towards the same destination, towards the same y value, we know our limit exists. So number one, find the limit as x approaches -3. So I see that there's a hole at -3, but I'm going to highlight points on both sides of -3. And I'm going to draw an arrow towards -3 along the path of the graph. And are the arrows headed towards the same y value? Yes, they're both headed towards what? A y value of 2. And so that's our limit. F of -3, that is just simply looking for the location at that point. The hole is undefined, but we do have a point defined at y value of 1. So Number 3, limit as x approaches -3 from the left side of -3. That means we're only following the path of the arrow to the left of -3. So we pick that means we're starting at a point to the left of -3, and then we're headed towards -3. So we're just following what the path this arrow is telling us. It's only a one-sided limit. This is headed towards 2. And then if we pick out the other side, the other arrow on the other side of -3 is also headed towards 2. So this also goes to highlight that if the one-sided limits are in agreement, then that means the full limit does exist, right? That means if both arrows are individually headed towards the same y value, then the true limit, the full limit does exist. All right, try 5 through 12. See if you can remember your process there. We can check our answers. And again, I have your key attached at the end of your packet. Okay, check your answers. Any questions here? Okay, talking about limits here. We know that, let me just kind of go through the process here. Initially, before L'Hopital's rule, we would have that option of either factoring or conjugate method or complex fraction. But now that we have L'Hopital's rule, I think we prefer L'Hopital's rule because it just goes a little bit faster. But just make sure that if you want to do L'Hopital's rule, that you're always doing direct substitution first, that we don't just jump into, oh, every limit problem can be L'Hopital's rule. You only do L'Hopital's rule if you get an indeterminate form. You've got to get a 0 over 0 from direct substitution to indicate that there's a green light to do L'Hopital's rule. Okay, because if you get a real number, then you should stop. That's your answer. If you get a vertical asymptote, you know there's or if you get a 10 over 0, you know there's a vertical asymptote, the limit doesn't exist. And we don't do L'Hopital's rule if the limit doesn't exist. So first steps first. Remember, sometimes the one-sided limit algebraically can just be a distraction. It doesn't play a role. We don't do any decimals unless there's a vertical asymptote. Right? Otherwise, it is just kind of distraction. So just do your direct substitution with your integer value. So what does the numerator get us? 0. Denominator, we get 0. Now, we could go through factoring process and cancel out the x minus 3s, but I think we probably prefer L'Hopital's rule, especially if the power rule can be fast. So numerator's derivative can be what? 1. Denominator is 2x minus 2. Now we can reevaluate. Again, no decimals, right? Just the integer value. And we get what? 1 over 4. That's a real number. That's our limit. All right, number 2. What's our first step? For substitution, okay, numerator we get. What do you get in the numerator? -5. Denominator, we get 0. All right, what does that tell us? What's happening here? Vertical asymptote. So normally we would say the limit what? The limit doesn't exist. But is this asking for the full limit? No, it's asking for the one-sided limit. So now we know that if we're approaching a vertical asymptote, there's only two things the graph can do, right? It's either going to go up to positive infinity or it's going to go down to negative infinity. So then the question is, how do we decide between these two? Without a calculator, we're going to rely on decimals. Okay, so now decimals will play a role. Right? What decimal can we choose that is close enough to the left side of 3? Sorry, to the left side of -3. Yeah, -3.1. And this can be done easily without a calculator because we don't have to get the exact value. We just care whether we get positive or negatives in our numerator or denominator. So 2 times -3.1 plus 1 over -3.1 plus 3. All right, numerator is going to be -6-ish plus 1, which is still what? Negative. Denominator is negative. 2 negatives makes positive. So it's only asking for the one-side limit towards an asymptote. We know the full limit doesn't exist, but we know that it's only asking for the behavior as we are approaching that asymptote. All right, number 3, our process shifts if we're approaching positive or negative infinity. We no longer plug in the x value. What do we do if we see infinities? What do we do? Compare degrees, right? This is end behavior. So just to remind us, if we compare degrees, if the denominator has a higher degree, your limit is always 0. If your degrees are the same, then it's just a ratio of the coefficients. If your numerator has a higher degree than denominator, then your limit doesn't exist. It's either positive or negative infinity. And then you can just plug in a large number to decide which direction it's headed. So what do you notice with number 3? Degrees are the same. The limit is just what? -1/5. All right, try number 4. First steps first. You should get 0/0, which gives you the green light to do L'Hopital's rule. Sine becomes cosine. Natural log of u becomes u prime over u. Now that you have your derivative version of your expression, replace all the x's with 0, and you should get 1/2, which is our limit, 1/2. All right, page 2. Anytime there's mentions of continuity, I think it's best to just go through the stepping through continuity conditions and just decide where the problem either fails, or if you're looking for a variable, you can go through continuity conditions. So the 3 conditions for continuity is: does a point exist? Does a limit exist? And sometimes we may have to delve into looking at both one-side limits to see if they're in agreement. And finally, if it passes the second condition, we look at the third condition, which is, does the limit live where the point lives? So once you get past the second condition, you're not doing anything new with the third condition. Third condition, you're just looking back at what you've gathered and seeing if there's agreement between the point and the limit. Right, so just run through number one real quickly. So it's giving us a piecewise function, and it's asking, is the function continuous at x equals -3? Well, let's just step through everything at -3. So we first need to figure out, does the point exist at -3? We plug -3 into our f of x function, which is part of my g of x piecewise. That gives us 4. So passes the first condition. Second condition, does the limit exist at -3? We see that there's a split definition on either side of -3. So we just do a one-side limit on both sides of -3. Plug in -3 on one side, we get 4. Plug in -3 on the other side, we get a positive 4. These are both in agreement. The limit does exist at 4. So now it passes the second condition. The third condition is just simply saying, do these agree? And they do. The point lives where the limit lives. And so therefore, everything is in agreement. My function is therefore continuous at x equals -3. Okay, we do need to start working through this packet here. So your homework is just pages 1 through 4. You have the key attached to the back. I'll send out a reminder this afternoon. All right, come get your phones. I know.
Yeah, like. Yes. Oh, wait.
Just send them.